is called On the Convergence of Monte Carlo Methods with Stochastic Gradient. So please, Chan, take it away. Thanks.
Thank you. Yeah, thank you. So it's my great pleasure to be here. So it's a wonderful workshop, a lot of great talks. So in this talk, I'm going to talk about the convergence analysis of Monte Carlo method with stochastic gradients. So this talk is based on the joint work with my student Difan Zhou and my former PhD student Pan Xu. He's now a postdoc at Caltech and will join the biostats department at Duke. So we've seen a lot of sampling problems in this workshop. The goal of sampling is to generate a sample from some target distribution. And one of the sampling problem we've seen a lot in this workshop is called sampling from the log concave distribution, where the target distribution can be represented by this Gibbs distribution, e to the power minus of f of x. And this f of x could be strongly convex and smooth. So I will talk about the assumptions later. And one of the applications of sampling from log concave distribution is in large-scale Bayesian learning. So suppose we have a set of data or observations zi I from 1 to n, which is drawn from some underlying data distribution, and we want to do Bayesian inference to calculate the posterior or to sample from the posterior, which is proportional to the product of the likelihood function defined on the data set and the prior distribution P of x. And with some linear algebra, we can easily show that the target distribution pi here can be written as e to the power of minus f of x, where this f of x is the summation of n individual functions f1 to fn. So each fi here is just the negative log density of each observation minus some log density of prior distribution. Okay, so this is the one particular application of something from log concave distribution. And in order to do that, there are a lot of MCMC methods we can use in. So for most of them, we can describe them in the following very generic form. So it is an iterative numerical algorithm. Given some initial sample, let's say x0, we keep generating new samples from the current sample. For example, suppose the current sample is xt, we generate xt plus 1 by randomly perturbing the current sample, or you sample some distribution, which is defined based on the current sample and perhaps also the underlying distribution function. That's why I use this g sub f of xt to mean that this random vector can depend on both xt and also the function, the negative log density function. And once we have the new sample xt plus 1, we can accept it or we can reject it with certain probability. And this probability is also defined based on the current sample, the new sample, and also the underlying target distribution. Okay. And examples of MCMC methods that can be described under this framework include, for example, random walk, Metropolis, ball walk, Mala, and HMC, and many others. So we've seen a great talk by Santosh yesterday, which is discuss different kinds of sampling method, and many of them can be unified under this generic description. And in my talk, I will be focusing on two particular MCMC methods. One is HMC, the Hamiltonian Monte Carlo. The other is underdamped Langevin dynamics. So for HMC, we know we first write down the Hamiltonian energy function, and then we solve the following system of differential equations. Then we will have the solution to this system of ordinary differential equation will give you two Markov process xt and vt. So here x is the position and p is the velocity. Okay, so by doing this kind of integration, you can calculate the idealized HMC dynamic although this is not the algorithm we are using, but in the convergence analysis, we highly rely on the connection between the discrete time algorithm and the discontinued time dynamic. And the nice property about HMC is if you can solve this dynamic exactly, then we can prove that when t go to infinity, the marginal distribution of the position parameter xt will converge to some distribution, which is the marginal distribution of the, which is the target distribution. And another very related MCMC method is underdamped Langevin dynamics, which is described by the following two differential equations. The first one is a stochastic differential equation. This is the friction term, the potential term, and also the Brownian motion. And the second one is just the ordinary differential equation. And if you remove the friction term as well as the Brownian motion term, actually, it will reduce to some differential equation, which is very similar to HMC. But it doesn't mean HMC is simpler than underdamped Langevin in terms of analysis. And similarly, we can also calculate the idealized or the continuous time underdamped Langevin dynamic by doing this kind of exact integration. Okay. Here's the question we need to think about when we apply this HMC or underdamped Langevin to the real sampling problems. For example, the large-scale Bayesian learning problem I just described a few minutes ago. You know, in order to apply HMC and underdamped Langevin, because both of them are gradient-based MCMC methods, we need to calculate the gradient. But when the data set is very large, for example, the n is the number of observations is very big, calculating the gradient, the full gradient, will be very expensive computationally or even intractable. Okay, and in order to overcome this problem, a very natural idea is to use the stochastic gradient to approximate the full gradient, and this gives rise to stochastic gradient version of HMC and underdamped Langevin. Okay, and the key question I want to discuss in this talk is how to prove the convergence of HMC and underdamped Langevin with stochastic gradient estimators. So when I say stochastic gradient estimators, it is a very broad family of stochastic gradient estimators, including, for example, mini batch stochastic gradient or variance reduced stochastic gradient. So it's a family of stochastic gradient estimators. It's not just a mini batch stochastic gradient. Okay, so here is a algorithm when you replace the gradient by stochastic gradient in the very standard HMC algorithm. Okay, so this algorithm has two loops. The inner loop is doing this leapfrog numerical integration, and the outer loop you just keep generating the random, for example, velocity, and from the current sample xt you do this leapfrog numerical integration for let's say k number of times, and then you assign the generated qk to be the next xt plus 1. Okay, so there are two index. The outer loop is indexed by t, the inner loop is indexed by k. Okay, and we don't do metropolis hasting here because we want to avoid the calculation of full gradient, also the calculation of the exact function value, because when you calculate the function value, you also need to calculate the function value for each fi, which might also be time consuming. Okay, and in order to prove the non-asymptotic rates for this kind of algorithm, we need to answer two questions. The first question is about the inner loop. What is the approximation error of the leapfrog integration using stochastic gradients? And the second question is about the outer loop. Can the approximate ODE solution provided by the leapfrog integration lead to small sampling error? Okay, so in the next few slides, I will answer these two questions by showing you very clean and beautiful, clean and simple analysis to answer these two questions. So before that, let me first lay out a few assumptions, which are very standard assumption. The first assumption is F is mu strongly convex, which means the target distribution is strongly log concave. The second assumption is F is L smooth, which means the target distribution is log smooth. And I denote this kappa, which is the ratio between L and mu as the condition number. Okay. And I also assume the stochastic gradient estimator has bounded the variance, which is bounded by sigma square. But for different stochastic gradient estimators, I will show you that this sigma square can have different dependence on the, for example, step size, dimension, and such and such. So which I will show you in a few minutes. So the proof is based on the following three sequences. The first sequence is the algorithm sequence. It's a discrete time algorithm. I introduce some shorthand notation, this S eta, which means I just run HMC with stochastic gradient with step size eta from QK. Then I get QK plus 1. And similarly, when I apply this S eta to PK, I will obtain PK plus 1. So this is essentially the algorithm, the discrete time algorithm. The second sequence is the HMC with conditionally expected gradient. Okay, so in other words, I define this G sub eta notation. When I apply this G sub eta notation to QK, I will get this conditional expectation of QK plus 1 conditional on PK and QK. And similarly, when I apply this G sub eta to PK, I basically doing this conditional expectation of PK plus 1 conditional PK and QK. Okay, but this does not give you the full gradient because in the leapfrog integrator there are 3 steps, and the first step and the third step involves the stochastic gradient. So the stochastic gradient actually is nested. So when you take a conditional expectation, it does not give you the full gradient. And the last sequence is the exact, the idealized HMC dynamic. This is a continuous time dynamic. And the goal for the inner loop analysis is to bound the approximation error, which is nothing but just the difference between the first sequence and the third sequence. The second sequence is some auxiliary sequence we introduced to ease the analysis. All right. Now, let me define some augmented variable zk. We just concatenate the position variable qk and also the velocity variable pk together. And the pk is normalized by square root of L. L is the smoothness parameter. This is just for the purpose of proving the bounded expansion property. So you can think of there's a Lyapunov function where the quadratic norm is normalized by 1 and this 1 over square root of L. Okay, and with a slight abuse of notation, I just use this same S sub eta operator. Now I just apply it to both Q and P. Okay, this is a slight abuse of notation. And from Z0, if I apply this operator for K times, then I use this S sub eta super K notation to denote that I apply this S eta operation for K times. And similarly, I use the same notation, convention for H and G operator. So this is a decomposition error. And first of all, I subtract and add back the same quantity. So this quantity is starting from Z0, you run K minus 1 step of HMC with stochastic gradient update, followed by another HMC update, but using the conditional expected gradient. So this is the meaning of this quantity. And based on conditional independence, this norm square expectation equal to the summation of these two guys. And if you look at this term is nothing but just the one-step statistical error between the stochastic gradient and the conditional expected gradient. I will choose K later. K and eta, so I will choose the step size such that even though there are some coefficient which is greater than 1, but by choosing the step size, I will make that coefficient to be a bigger 1, a constant. So in that case, the approximation error will not grow as K grows. This index K is the index of the inner loop. Yeah. So little analysis is still inside the inner loop, the leapfrog integration part. So this can be bounded by this order, L1 divided by L, sigma square, eta square. So sigma square is the variance of the stochastic gradient. L is the smoothness parameter, and eta is the step size. And this guy, by further subtracting and adding another interesting and related quantity, which is h eta s sub eta k minus 1 z0. So this guy is, you start from z0, you run k minus 1 step of HMC with stochastic gradient, followed by another step of HMC, but using the integration, the exact update. Okay, and then we are using the Young's inequality to bound this term by the summation of these two terms. And the notion of Young's inequality we are using is this 1 plus alpha and 1 plus 1 divided by alpha version, because we want to have some additional degree of freedom alpha to bound this quantity. Okay, and now let's take a closer look at this term. So this term, it is nothing but just the discretization arrow, because you can see from S sub eta k minus 1 z0 from this point, the same point, if you do, for example, conditional expected gradient update, or if you do the exact update. So this is something sort of the discretization arrow. Okay, and the remaining thing is to bound this term. And in order to bound this term, we can fill this term as starting from two different points. This blue point and this red point denoted here, applying the same operator h eta. Okay. Unfortunately, we don't have a contraction property for this h eta, but we have some good enough property, which is bounded expansion property for this h eta operator. So we can show that the expansion coefficient can be bounded by e to the power of 2 times square root of L times eta. And using this property, we can bound this term. And by putting these several pieces together, we will have the approximation error after K leapfrog integration is upbounded by this expansion term, which depend on the approximation error after K minus 1 step of leapfrog integration, but using stochastic gradient, plus this one step error, which is the sum of the one step approximation error and also a one step statistical error and also one step discretization error. Okay. And using some very simple inequality, we can move this 1 plus alpha into the exponent of this exponential function. And now we need to choose alpha, because alpha is the parameter we introduced when we apply the Young's inequality. So here we need to choose alpha. We choose alpha to be in the same order of this guy. And then we choose K times eta, because K times eta appears in the exponent of the exponential function in the numerator, but we want this numerator to be a bigger 1, right? So we choose K eta is less than or equal to 1 divided by square root of L. And in this way, we can make this numerator to be a constant. And also we just divided by this term by the denominator. We do some simplification, then we get this arrow. So this is the approximation arrow after bigger K number of leapfrog integration with a stochastic gradient. It doesn't depend on K. So this is the thing we want to this is the bound we want to attain, because if we depend on k, then the error will explode. Any question? Okay. Now we have the approximation error bound for the inner loop. I will talk about the convergence for the outer loop. And the convergence for the outer loop actually is based on some contraction property proved by Chen and Santosh in their very nice paper. So we basically consider these two Markov chains, and we are doing some kind of coupling. So each element in this HMC with stochastic gradient Markov chain is just the initial sample, and the sample after the first inner loop, the sample after the second inner loop. So this is the first chain, and the other chain is just the idealized HMC. Every time you just you initialize it from the sample from the target distribution. Okay, and using this nice contraction property, but I want to comment that this property, when you use it, you be careful because it only holds for any 2 points with different position, but with the same velocity. So this contraction property does not hold for any QP or Q prime P prime. So the velocity need to be the same. Okay, we have this contraction, and then we further apply another Young's inequality, and combining this on this sampling error by this contraction error as well as the approximation error we proved in the inner loop analysis. Okay, and then with some parameter choice, we are able to prove this main result. So this is the convergence rate of stochastic gradient HMC for any stochastic gradient estimator with bounded variance sigma square here. Okay, and now let me showcase some applications of this general result when we apply it to different stochastic gradient estimators. So we can apply it to mini batch stochastic gradient, or we can apply it to ACVRG, which is a variance-reduced stochastic gradient estimator, or this stochastic average gradient called SAGA, or control variate gradient. Due to time limit, I will just focus on the first two. And for the remaining result, you can find it in the paper. So mini batch stochastic gradient, I don't think I need to introduce it. Everyone knows it. You just sample a subset of data points and calculate the gradient on that subset. And for ACVRG, it's a very nice algorithm. So there's it's actually an epoch-wise update. So the epoch length is this big N. So after big N number of samples, you will store that sample as a reference sample and use the full gradient at that reference sample as a reference gradient. And within the epoch, or between any two reference points, you are going to calculate this so-called semi-stochastic gradient, which is the difference between two mini batch stochastic gradient at the current sample and the reference sample. And then you plus the full gradient at the reference sample. So you can show that this semi-stochastic gradient, first of all, is unbiased. Second, the variance actually will decrease when the distribution of QK and Q2 getting closer and closer to each other. And based on the assumptions I laid out before, we can show that the variance of a mini batch stochastic gradient is bounded by n squared. N is the number of observations divided by b. B is the mini batch size times some quantity, which is the expectation of the each individual gradient of each individual function at x star. X star is the global minimum of the negative log density function. And for ACVRG, actually, we can show that the variance can be bounded by L squared divided by B and times N squared D and eta squared. So this N, remember that this big N is the length of the epoch in ACVRG. Okay, now we can also calculate the variance bound for the other two stochastic gradient estimators, which I just omitted here. And by substituting this variance bound into this master theorem, and then do some calculation, we can prove the query complexity of stochastic gradient HMC with different kinds of stochastic gradient estimators, including mini batch, stochastic gradient, or variance-reduced stochastic gradient, or control-variate gradient. And you can say that if I'm using variance-reduced stochastic gradient, the query complexity, the number of queries to the gradient of each fi. So this is considered as one query. So the query complexity actually has a sublinear dependence on the number of observations. It's like n2 2 divided by 3. And also the epsilon, the sampling error also has a sublinear dependence, like 1 divided by epsilon 2 divided by 3. Okay, and you can do a more careful comparison, for example, with variance-reduced overdamped Langevin dynamic, which is n divided by epsilon. But in terms of dependence on both n and epsilon, actually our result is strictly better. So this is something I want to talk about. And in the next 5 minutes, I will just show that similar analysis can be applied to underdamped Langevin dynamic. Actually, we did this work 3 years ago. At that time, the proof technique we use is slightly different and is more complicated. But now, using the same proof roadmap, we can simplify the proof a lot, and which gives you some easy to follow analysis. So remind you, so this underdamped Langevin is a SDE I just introduced before, and following Chen et al., we can partially solve this SDE to generate some kind of implementable dynamic. And the key here is we need to replace the full gradient by the stochastic gradient. And this introduces some challenges when you prove the convergence. But we can follow the same proof roadmap. We introduce 3 sequences. And here I want to comment that the second sequence, the auxiliary sequence, which is the conditional expected gradient. In this case, actually, it is equal to the exact gradient. Because in underdamped Langevin, the stochastic gradient, there's only one step stochastic gradient in each iteration. Okay, and we can do similar sampling error decomposition, which I'm not going to repeat here. But I want to mention that this ZK actually you need to define it in a slightly different way. So this ZK is a concatenation of XK and XK plus VK. This is also shown in Chen et al. Paper because they found that by constructing this kind of augmented parameter, you can have some real function that will lead to contraction. And compared with HMC, the nice thing about the underdamped Langevin is the contraction property proved by Chen et al. Hold for any 2 points Z and Z prime. Okay, but before, remember that in HMC, the contraction property only holds for any 2 points with different position but the same velocity. Okay, and because of this, it will also simplify the analysis in some steps. And let me directly show the main result we proved. The reference is the 2018 SML paper, and also Chatterjee et al. They also have some result for control-variate underdamped Langevin. And I believe in Chen et al. Paper, they also have the mini-batch version. But the result we proved using the new technique gives us exactly the same result. But this result we have proved using some different, more complicated one several years ago. So you can see that we just plug in those variance bound into this master theorem, and then we can derive the query complexity for underdamped Langevin with stochastic gradients. And interesting observation is you can just compare line by line, for example, stochastic gradient underdamped Langevin with stochastic gradient Hamiltonian Monte Carlo. So they have the same query complexity. And also for HVRG or Saga underdamped Langevin and FZRG or Saga HMC, they have the same query complexity. Of course, in terms of the dependence on the condition number, there may be some minor difference because we didn't try to sharpen the dependence on the condition number. Because in our result, complexity result, we treat kappa as a big O1 as a constant. Okay. All right. So to summarize, we provide a unified analysis for HMC and the underdamped Langevin with stochastic gradients. And the analysis is based on 3 sequences of Markov chains. And something I already mentioned is when you utilize the contraction property of HMC and the underdamped Langevin, they are different in terms of either it holds for any 2 points or holds for any 2 points with the same velocity. And also the contraction property holds at different level. For underdamped Langevin, it holds for every iteration, but for HMC, the contraction property only holds in every k iteration, so only holds in the outer loop rather than the inner loop. And what's next? So one thing I think might be interesting to look at is if the target distribution is not strongly log concave or even log concave, for example, non-log concave. In that case, the contraction property does not hold, and how to control the approximation error of this kind of numerical solver could be an interesting problem to think about. So there are some prior work by Rodzinski and Fampler and Wipsner and many other people. They relaxed the contraction to be a weaker version based on log Sobolev inequality or Poincaré inequality and such and such. And another direction is at the beginning, I mentioned that I removed the Metropolis Hastings correction step because I don't know how to come up with a stochastic version or stochastic estimate for the rejection or acceptance probability. But in one of the talks in this workshop, I see they're using some very clever idea to construct a nearly unbiased estimator of the Metropolis Hastings probability. So that might be an interesting thing to think about if we can combine this Metropolis Hastings step with the current stochastic gradient algorithm. So that's all I want to talk about. Thank you for your attention.
Thank you, Chen-Chan, for the nice talk. Are there any questions?
Is your analysis tight for some of the SVRG variants? I mean, the stochastic gradient variants. So for example, the n to the 2/3 over epsilon to the 2/3.
Yeah, we believe it is tight because if we are familiar with the result for convex optimization using SVRG, there are this kind of dependence also showing up. But the key challenge is here we are sampling from strongly log concave distribution. In optimization, there's, for example, Nesterov accelerated gradient, also called accelerated SVRG or Kachusa, some kind of algorithm, which can give you a better gradient complexity result. So it's possible that if we are not using SVRG, but using some accelerated version of SVRG, we might be able to reduce the dependence, this dependence on the number of observations. So that's, I think, is possible.
Thanks for the very interesting talk. So I know, Quanquan, you have also looked into second order methods for other applications. Do you think that this, variance reduced second orders or just generally like second order approach would work better here?
That's a great question. So I also talked to someone during this workshop because for second order optimization, if a function is, for example, non-convex, but if you are using, let's say, cubic regularization, you are still guaranteed to find the for example, local minimum if the function satisfies Hessian-Lipschitz property. And I know in the sampling literature, the Hessian-Lipschitz property is often also assumed in many papers, but I'm not sure what's the correspondence of escaping from saddle point or finding a local mean. What's the corresponding part in sampling? This is something I haven't fully understand myself. Maybe someone knows, you can teach me, but I don't know what's the correspondence of escaping saddle point in the sampling process. In optimization, we know we want to find the local minimum or even global minimum. If we hit a saddle point, we can use the negative curvature direction to escape from that saddle point using either cubic regularization or using some like perturbed gradient method. But in sampling, if we we already have some, for example, Brownian motion, which is also kind of a random perturbation. And with that, random perturbation play some role in terms of escaping the saddle. And what's the meaning of escaping the saddle in sampling? Is it still meaningful, or is it well defined? So this is something I don't quite, I don't have a good understanding. So I'm happy to discuss with you offline, or yeah.
Any other question? So maybe I have one. So earlier this week, so Chin Lee gave a talk about a coordinate using, instead of the full gradient, taking sampling coordinates. And I was wondering, how does the analysis that you present here compare to the work of Chin Lee and Steve Wright? If you're familiar with that.
I think at a high level, it should be similar, but our work is in 2018 is earlier. So I need to take a closer look at their proof, but I believe this kind of Fourier introduction technique, the proof should share a lot of similarity. Okay, but their Fourier introduction is not in the sample dimension. Actually, it's in the coordinate dimension. So there might be from a different angle. So I need to take a closer look before I can tell you the exact difference. Yeah.
Thank you, Chen Chen. So let's thank the speaker again.
Thank you.
Then we resume at 4 o'clock.